Hello and welcome to this revision video for AQA Chemistry Paper 1. If you'd like to, you can download handouts at gcserevisionmonkey.com. Topic 3 is called Quantitative Chemistry, which involves a lot of different calculations. Now for foundation tier, the only subjects you need to know about within this topic are relative formula mass, percentage mass and conservation of mass. However, there are several higher tier only topics which I'll also talk about, and for higher tier this tends to be the topic that people find most difficult when it comes to the exam. Starting with relative formula mass, there's a clue with what you need to do. You need to calculate the mass of a chemical formula. So starting with this question, it says calculate the relative formula mass, or MR as we call it, of H2O. So we need to find the mass of that formula. So first of all, we need to know how many atoms of each element there are. If we look at hydrogen, it's got the number 2 next to it. So we know that there's 2 atoms of hydrogen and there's just 1 atom of oxygen. So we need to find the mass of the whole thing. In the exam, you'll be given a data sheet with a periodic table. Apologies if this one's a bit blurry, I've just blown it up for you. On the periodic table there's a key, so it will tell you that the top number is the mass, then you've got the symbol, the name, and the bottom number is the protons. So it's the mass number we want, it's the top number. So never guess, always look at this key to help you. So we need to find the mass of hydrogen and the mass of oxygen. The mass of hydrogen is 1 and the mass of oxygen is 16. So to calculate the relative formula mass, we would do 2 lots of 1 and add that to 1 lot of 16. And that will give you the relative formula mass of 18. And we're going to do exactly the same thing now with some other examples. So you'd use your data sheet again to find out the masses of these. So we've got 1 atom of calcium, and the mass of calcium from the periodic table is 40, and we add that to 2 atoms of chlorine, for which the masses are 35.5, and if you add that together you'll get a relative formula mass for calcium chloride of 111. Calcium carbonate down the bottom here, we've got 1 atom of calcium, 1 atom of carbon and 3 of oxygen. So on the periodic table, the mass of calcium is 40, so we need 1 lot of 40, added to 1 lot of 12, added to 3 lots of 16, and that will give you the relative formula mass of 100. So it's simply adding up the masses of all the atoms that you have. The one complicated thing is when you have things in brackets. Things in brackets mean that they are multiplied by the number outside of the brackets. So in this example, you just have 1 magnesium because it is not within the bracket, but oxygen is within the bracket, so you'd have 2 lots of oxygen and you'd have 2 lots of hydrogen. So to calculate the relative formula mass of this one, it would be 1 lot of magnesium, which is 24, added to 2 lots of oxygen, added to 2 lots of hydrogen. The mass of oxygen is 16, the mass of hydrogen is 1. And if you add all of those together, you would have a relative formula mass of 58. Linking to relative formula mass, you might be asked to calculate percentage mass, and you might see a question such as this, where it says calculate the percentage by mass of hydrogen in water. And to do this, you calculate the mass of hydrogen that's in the molecule, divided by the whole thing, multiplied by 100. So from our periodic table, we'd find the mass of hydrogen is 1, but we've got 2 lots of that, so we need to do the mass of hydrogen divided by the relative formula mass of the whole thing, which would be 16, plus 2 lots of 1, which would be 18, like we worked out earlier. and then we would multiply that by 100. So just to show you the working, we've done the mass of hydrogen divided by the relative formula mass of the whole of the water, and then multiplied by 100. So 2 divided by 18 multiplied by 100 would give us a percentage of 11.11%. Same for calcium carbonate then. Calculate the percentage by mass of carbon in calcium carbonate. There's the carbon. So the mass of carbon in there's just one of them. So on your periodic table you see the mass of carbon is 12, divided by the relative formula mass of the whole thing, which in this case is 40 plus 12 plus 3 lots of 16, which gives you 100, multiplied by 100, and that gives us the percentage as 12% carbon. We're now going to talk about conservation of mass, and this is where you might find a calculation question that on the face of it will appear quite difficult. For example, this one, whereby 73 grams of hydrochloric acid, which is down here, reacts with 100 grams of calcium carbonate to produce 111 grams of calcium chloride and 44 grams of carbon dioxide. How much water would be produced in the reaction? Now the key thing is to look at how many marks there are. If there's just 1 or 2 marks, it's going to require you to do a very small calculation and a very minimal amount of work. It's not asking you to do a higher tier mass calculation or anything like that. And it's simply just checking your understanding of the idea of the conservation of mass, which says the mass on the left-hand side of the equation, which in this case is 73 and 100, so 173, the mass of the reactants must equal the mass of the products. So here we've got 111 grams plus 44 grams plus whatever the mass of water is. So on this side, so far we've got 155 grams, and that can't be the case because it should be 173. And that's where we can find our mass of water. So if we take 155 away from 173, we will get our mass of water, which is 18 grams, and there's our answer. So a simple calculation to get our answer for the mass of water, even though the question looks very, very complicated. So I would recommend reading the question and then taking the numbers out of the question and writing them on top of the equation next to the right chemical, and then you'll realise that it will simply be a case of making sure that this side equals this side. You may also see conservation of mass discussed in an experimental way. For example, they might give you a particular reading on a balance and a reaction that's taking place on top of that balance. So here we've got a conical flask containing some metal and some acid. So for example, this could be magnesium and hydrochloric acid, giving off some hydrogen gas here. And the question says, what will happen to the reading on the balance? Well, in this case, we need to look carefully at the diagram. There is a lid on the conical flask, which means that none of the reactants or products will escape. So nothing will happen to the reading on the balance. It will stay the same. However, in this case, they might ask you to explain what will happen to the reading on the balance here. So the reading on the balance starts off at 25 grams, but you can see this time there is no lid on the conical flask. So the gas will be able to escape. Mass is escaping, therefore the reading will go down or will decrease. And you would need to explain the reason why and the fact that the gas is escaping and therefore mass is being able to leave the conical flask. In this example, what will happen to the reading on the balance? Well, there's another example that might increase the reading on the balance. For example, if this was a piece of metal, like magnesium for example, Gradually, over time, that reading on the balance might increase, and this is the one people get really confused about. They think, well, why is that going to go up if I'm just leaving a piece of metal on the balance? Well, it's all to do with the oxygen in the air. If the metal reacts with oxygen in the air, then oxygen will be adding to the mass of the metal, causing the reading on the balance to increase. So be aware of that situation. If a balance reading is going up and you're not sure why, generally it will be to do with the fact that oxygen in the air is reacting with the metal, creating a metal oxide adding to its weight. So you'd get magnesium reacting with oxygen, making magnesium oxide. This section on moles is for higher tier only. Moles in chemistry is a word to describe a particular number of particles, and that number of particles comes from Avogadro's constant, which is a very particular number of particles, 6.02 times 10 to the 23 particles. So 1 mole of a substance will contain 6.02 times 10 to the 23. It's just like using the word dozen to represent 12. We would say we have a dozen toy cars, for example, rather than saying we have 12 cars. Or rather than saying we have 6.02 times 10 to the 23 atoms of carbon, we shorten that by saying we have 1 mole of carbon. The mole is represented by the large numbers in front of chemicals in an equation. For example, this equation here we can write out in terms of moles, and you may be asked to do this in the exam. So here we would describe this as 2 moles of hydrochloric acid reacting with 1 mole of calcium carbonate to produce 1 mole of calcium chloride, 1 mole of water, and 1 mole of carbon dioxide. So this is what the large number is representing, the ratio of moles that you have in the equation. Moles relate to relative formula mass in the equation that we'll talk about on the next slide. However, quite simply, the relative formula mass in grams is how much 1 mole weighs. For example, the relative formula mass of calcium carbonate from the previous slide we worked out as 100. So it has a relative formula mass of 100. So 1 mole of calcium carbonate would equal 100 grams. Whereas water, we said, has a relative formula mass of 18. So 1 mole of water would weigh 18 grams. Or if we talk about it in terms of the number of particles, we're saying 1 mole, so 6.02 times 10 to the 23 particles of calcium carbonate would weigh 100 grams, or 1 mole, which is 6.02 times 10 to the 23 particles of water, would weigh 18 grams. This equation here is one that you're definitely going to have to remember, and I would highly recommend you writing that down as soon as you get started in your exam. Just turn over the first page and then a piece of blank space, write down moles equals mass divided by mR, because it's likely that you will need that in your exam. So questions such as this: how many moles are there in 16 grams of carbon dioxide? Well, if moles equals mass divided by mR, we would need to work out the relative formula mass of carbon dioxide. Using our periodic table, the mass of carbon is 12 and the mass of oxygen is 16. So 16 times 2, because there are 2 oxygen atoms in there, will give you a relative formula mass of 44. So how many moles are there? Well, moles equals mass divided by mR, so 16 divided by 44 would give you the answer of 0.36 moles. Second question, how many moles are there in 2 grams of calcium carbonate? Well, the relative formula mass of calcium carbonate, if you were to work that out, is 100 because we've got 40 added to 12 added to 3 lots of 16. So moles equals 2 divided by 100, which will give the answer of 0.02 moles. Another topic for higher tier students only is balancing equations using masses. Now hopefully you'll be able to balance equations the standard way, but this question is all about getting marks for your working out. It says write a balanced simple equation for 46 grams of sodium reacting with 16 grams of oxygen to form 62 grams of sodium oxide. Now what they don't want you to do is just write down sodium reacting with oxygen to get to sodium oxide. Now what they don't want you to do is just balance it using just the equation. So you could just have a look at the equation and balance it yourselves, but that's not what they want. They want you to show the working out. But the nice thing is if you can do this, you will know that you'll get the right answer at the end of it. What they want you to do is start off with the masses, so 46 grams of sodium reacting with 16 grams of oxygen, producing 62 grams of sodium oxide. What they want you to do is divide these masses here by the relative formula mass. And if you're doing mass divided by relative formula mass, like we've looked at previously, you're working out the number of moles, which is the numbers that we put in front of a balanced equation. So 46, the relative formula mass of just sodium on its own is the relative atomic mass of sodium, which is 23. The relative formula mass of oxygen is 2 lots of oxygen. So on the periodic table, oxygen has a mass of 16. 2 lots of 16 is 32. And sodium oxide, we need 2 lots of 23 plus 1 lot of 16, all from the periodic table, and you will see that that has a relative formula mass of 62. If we divide those up, we get a ratio of 2 to 0.5 to 1. But we can't leave a decimal point in there. We have to make whole numbers. So if we multiply each number by 2, that will give us a whole number because we need to get this one to 1. So if we multiply everything by 2, we should end up with whole numbers. So we've got 4 to 1 to 2. And then we can just write our balanced equation when we're there. So we can write it back in. 4Na plus O2 makes 2Na2O. And we know when we're at this stage that we've got the right answer because we have got our balanced equation that we knew we would get to before. So if you get stuck, try writing the balanced equation out like this, then show all the working out to show that how you got there using the masses. So we're using that equation again, moles equals mass divided by relative formula mass, but this time to balance an equation. Mass calculations is a topic for higher tier pupils only. This is a typical question that they might ask you. Calculate the mass of carbon dioxide produced when 50 grams of sodium carbonate reacts with hydrochloric acid. So I always tend to write the masses underneath. So this is the sodium carbonate. The question says if we've got 50 grams of this, how much carbon dioxide are we going to make? This, in this case, is what we describe as our limiting reactant. We've specified the amount of sodium carbonate that we're reacting, and when that's all used up, the reaction will stop. So that's our limiting reactant. And we actually don't need to worry about anything else in the equation. So I'd cross through all those other things, because really we just need to know about the two things they've asked us about, carbon dioxide and sodium carbonate. So when 50 grams of that reacts, how much carbon dioxide are we going to produce? It doesn't matter whether this was 50 grams, 50 tons, 50 kilograms. we do the same method for whatever unit there is. So first of all, what we can't do is just guess. We can't just guess a number that 50 grams might make, but we do have information on the relative formula masses that we can calculate from the periodic table. First thing to do is make sure the equation is balanced, and we can just check here. We can see that it's already been balanced. So there's going to be 1 mole of sodium carbonate and 1 mole of carbon dioxide. So if we use the periodic table, the relative atomic mass of sodium is 23, and there's 2 lots of those. Add that to carbon, which is 12, and add that to 3 lots of oxygen, which is 16. That will give us a relative formula mass of sodium carbonate of 106. And using the periodic table again, carbon is 12, 16 times 2, that will give us a relative formula mass of 44. So straight away we can say that 106 grams of sodium carbonate would produce 44 grams of carbon dioxide. If we then get this down to 1 by dividing it by itself and do the same thing to the other side, divide by 106, we will get 1 gram of sodium carbonate equaling a very long number in the calculator. You can keep it in the calculator, but I'll just write it out so that the answer works out right. 0.41509434. But we don't want to know what 1 gram will produce. We want to know what 50 grams would produce. So to get from 1 to 50, we would multiply by 50. And therefore we will get to the answer that 50 grams would produce 20.754717. So I'm just going to put 20.75. In the exam they'll tell you what decimal place or significant figures to put it to, but grams of carbon dioxide. So to recap then, you calculate the relative formula mass. Before that, check the equation is balanced. Check the equation is balanced, and then calculate the relative formula masses. Divide by itself to get to 1, and then multiply to get what the question has asked you for. Okay, what they might do is start off with a number on this side. So for example, they could have switched that around and said, how much sodium carbonate would you need to make 50 grams of carbon dioxide? And you do exactly the same process, but this time it would be this side of the equation that you'd want to get down to 1 and then multiply up. So they could ask you both ways around. Concentration calculations is for higher tier pupils only. So this is another equation that I suggest you write down as soon as you get into the exam. On any piece of blank space, we said to write down the moles equals mass divided by relative formula mass. Also write down concentration equals mass divided by volume. And I would also suggest writing down the units that go along with that. So concentration is measured in grams per decimeters cubed. So therefore the masses that you're using have to be in grams, and the volume that you are using has to be in decimeters cubed. If you remember the units, you'll remember they tell you that you need to do the substance that's in grams divided by the number that's in decimeters cubed. So for example, this question here, what's the concentration of a sodium chloride solution made from 3.5 grams of sodium chloride dissolved in 0.3 decimeters cubed? So in this case we do 3.5 divided by 0.3 and we get an answer of 11.67 grams per decimeters cubed. They may well in the question ask you to write that to a particular significant figures. For example, if it says give your answer to 2 significant figures, that would be 12 grams per decimeters cubed to two significant figures. So do look carefully for what they ask you to write down the answer in. Second question here, what's the concentration of a sodium chloride solution made from 5 grams of sodium chloride dissolved in 20 centimetres cubed? Now this is where people make mistakes and lose marks. They just see this and think to themselves, okay, I just need to do 5 divided by 200. But you don't, because you must notice that this volume that they've given you in is in centimetres cubed, not decimetres cubed. So to get to decimetres cubed, you need to divide by 1,000. So you need to do that first of all. 200 divided by 1,000 will give you 0.2 decimetres cubed. You must do that step, otherwise you lose all of the marks. You then can carry on and do 5 divided by 0.2, and that will give you 25 grams per decimeters cubed. It's exactly the same thing. Check out for the units here. If they give it to you in kilograms, you must convert it to grams first of all before you put it into the equation. Otherwise, you will lose all of the marks. Topic 4 is called chemical changes. It includes a couple of required practicals on salts and electrolysis, and it also has quite a lot of high tier content which I'll highlight as we go through. First of all, we'll talk about neutralisation, and the general equation for neutralisation is when an acid reacts with a base to make a salt plus water. Now this base can either be insoluble, so something like calcium oxide where you'd have a powder that you'd add to your acid, or it can be soluble, something like sodium hydroxide, where you would have a liquid or a solution that you react with the acid. And soluble bases have another very special name called alkali. So if you see an alkali reacting with an acid, you know that that is a soluble base or a solution that you're using. When you react an alkali with an acid, you can use an indicator like universal indicator, or a piece of equipment like a pH probe instead, which is an electrical piece of equipment that will give you an exact number, because the universal indicator links with the pH scale. So this here is the pH scale. It goes from 1 to 14. Number 7 in the middle, pH 7, is for a neutral substance, for example water. So sometimes you have a pH 0 as well on the end here. The range 0 to 6 are your acids, so the range 0 to 6. And within the range 8 to 14 are your alkalis, 8 to 14. Now acids are solutions that have hydrogen ions in them, whereas alkalis have the ion hydroxide in them. So I'll just write that hydroxide out. Hydroxide ions for an alkali and hydrogen ions for an acid. Now with the neutralisation reaction, you're taking an acid and you're reacting it with a base to make a salt plus water. So if you're making an acid with hydrogen ions, react with an alkali with hydroxide ions, you can see that the result of those two reacting are going to make water. And also you'll make a salt in the reaction as well. But this is the ionic equation for neutralisation. So using the pH scale, we can describe acids that are far away from neutral as strong acids, and the ones that are closer as weaker acids. In the same way with alkalis, the closer you are to water and to neutrality, the weaker you are, and the further away you are, there's your strong alkalis at the end. This section on strong and weak acids is for higher tier pupils only. This section on strong and weak acids links again to the pH scale, so just in a little bit more detail. pH is a measure of the concentration of hydrogen ions in a solution. So we said before that here with our 0, our 1, these are our strong acids, and here are our weak acids. When you go down a number on the pH scale, you increase the number of hydrogen ions in your solution by a factor of 10. So that's something to be aware of. They might give you a certain number of hydrogen ions that are in a pH 6 solution and perhaps ask you how many would be in a pH 2 solution. You have to keep multiplying by 10 until you get to the right pH. So they increase by a factor of each 10 as the pH decreases. But the words strong and weak acids also refer to particular types of acid. Strong ones are the ones that you are probably used to using in your lab. So for example, hydrochloric acid, sulfuric acid and nitric acid. Note that they all start with H because they're all producing hydrogen ions. When they dissolve in solution, strong acids completely ionize in water. What ionizing means in this case is they completely break down into their two ions. For example, hydrochloric acid would completely ionize into H+ ions and chloride ions when it is dissolved in water. Whereas weak acids are things such as citric acid, carboxylic acids like ethanoic acid. And with these weak acids, they only partially ionize in water. Partially ionizing means that if you have, for example, ethanoic acid, which is CH3COOH, when that breaks down in water, it's actually a reversible reaction. You do get hydrogen ions and the negative part of the ion as well, CH3COO-. So it does break down and form hydrogen ions, but because it's reversible, these form again to produce ethanoic acid. So you get fewer hydrogen ions in solution. So in this case, you get more hydrogen ions, whereas with a weak acid, you get fewer hydrogen ions. And this will of course relate then to their pH on the pH scale. The more hydrogen ions that you've got, the stronger the acid, the fewer hydrogen ions, the weaker the acid. So this makes these strong acids more reactive as well, because there are more hydrogen ions in there that can then react. But also we can look at them in terms of the difference between strength and concentration, because we could have two bottles of acid with the same concentration, hydrochloric and ethanoic acid, and we can both, for example, have the concentration of 1 molar. They've got the same amount in grams dissolved per volume. Remember those units from concentration. So they've got the same amount of acid dissolved in solution. However, because this one will be completely ionizing in water, producing lots of hydrogen ions, this will be a stronger acid with a lower pH. Whereas this ethanoic acid here will only partially ionize in water, so it will be a weaker acid with a higher pH. There are several chemical reactions that you need to know of as part of this topic. First one that we'll look at is reactions with metals and water. So when metals react with water, they will produce a metal hydroxide and hydrogen gas. So potassium and water would make potassium hydroxide plus hydrogen. If you remember from when we looked at the periodic table, potassium will actually float on top of the water and perhaps will spark and flame as well because it's a reactive group 1 alkali metal. But this will work with any metal that will be able to react with water. So for example, you might have magnesium reacting with water, and this time you'll produce magnesium hydroxide plus hydrogen. Some metals are not reactive enough to react with water, like copper, so you wouldn't be able to write an equation for that, but anything that reacts with water you can. For the next reactions, many of them will produce something called a salt. So let's talk about how we name salts first of all. We name salts in two parts. They will have one part that is the metal that's in the salt, and the second part will depend on the acid. So there's three acids that you need to know about in particular. Sulfuric acid makes a sulfate salt. Nitric acid makes a nitrate salt. And hydrochloric acid makes a chloride salt. Okay, so those three we really need to remember because then we'll be able to name all of the salts in this exam. So this is an example of our first reaction that's going to produce a salt plus hydrogen. So if you put a metal in with an acid, you'll produce a salt plus hydrogen. Naming the salts then, we've got the metal iron, and this time we're reacting with hydrochloric acid. So following our rules, we'll make iron chloride plus hydrogen. Here we've got iron and sulfuric acid reacting, so we make iron sulfate this time, plus hydrogen. And finally we've got nitric acid this time, so we'd make iron nitrate plus hydrogen. If we change the metal, for example, if this was magnesium, instead we'd make magnesium chloride and hydrogen, and so on. In this reaction we are reacting acid with a metal oxide this time, so before we were just reacting it with a metal and producing hydrogen. Now we've got oxygen in there, we're producing water instead, so we're producing a salt plus water. So nitric acid and sodium oxide, there's the metal, sodium, and we're using nitric acid, so we're going to make the salt sodium nitrate, and our second product is going to be water. It's very, very similar, and we've got a metal hydroxide here. So whereas this was sodium oxide, which is Na2O, this time we've got a metal hydroxide, which in this case is iron hydroxide, which is FeOH2. So it's the OH hydroxide we've got now, but same way it produces a salt plus water. So this time the metal is iron and we're using sulfuric acid, so we make iron sulfate plus water. In this reaction we've got now a metal carbonate, and if you see the word carbon you must think to yourself that this reaction also produces carbon dioxide. So you've got hydrochloric acid plus zinc carbonate, and you're going to produce a salt plus water plus carbon dioxide. So let's name the salt first of all. The metal is zinc and the acid is hydrochloric, so we will make zinc chloride, and then we will make water, and because it's a carbonate we will also make carbon dioxide. Two further reactions, we've got oxidation and reduction. In terms of a chemical reaction, oxidation means the gain of oxygen, and reduction means the loss of oxygen. You also see these two words later on in terms of electrons, and they mean something different, but for the moment we're talking about a chemical reaction. So in this one, zinc reacts with oxygen, and zinc gains oxygen, so it forms zinc oxide. And in terms of reduction this time, it means the loss of oxygen. So this time zinc oxide would lose its oxygen. So you'd make zinc plus carbon dioxide. We'll now talk about the required practical, which is all about making a salt. So to make a salt, we're going to do a neutralisation reaction. So we've got our base reacting with our acid to make a salt plus water. In this case, we've got copper oxide reacting with hydrochloric acid to produce copper chloride salt and water. You could use sulfuric acid to make copper sulfate. It all depends on what salt that you want to make at the end of the process. So this copper oxide, you can see by the state symbol, is solid, it's insoluble, and it is a black powder. That will react with acid and make a soluble salt. You can tell by this state symbol of AQ, which means aqueous, that is soluble and it's going to be dissolved in water. So to start off with, to make our salt, we need to add the copper oxide in excess to the acid. Really important term, it means we keep adding it until no more reacts. So we have our acid in our beaker, certain amount, say 30 mils that we would measure with our measuring cylinder, and then we keep adding that copper oxide in excess until we see the copper oxide at the bottom of the beaker to show that no more can react. We now need to get rid of that, because if we were just to heat that, we wouldn't end up with our pure crystals, we'd end up with some copper oxide on top as well. So the first process is filtration. We'd pour that reaction into our filter paper with inside our funnel. And in the conical flask, we would collect our solution containing our salt and our water, and at the top here we would have our excess copper oxide collected and filtered out. The next process is to then get rid of the water, because we just want the salt on its own. So the next process is called crystallization, and you can either use a Bunsen burner to heat up an evaporating dish over a tripod. Sometimes you might choose to heat it up more slowly in a water bath, or using an electric heater. You might see any of those heating methods in the exam, but we put our solution into there and our water will evaporate. And that will leave us, after a while, we might take it off the heat and leave it to finish evaporating off the heat, but we will end up with crystals left in our evaporating dish where we've actually extracted our salt crystals. So you need to be able to describe this method and say each step by step what you need to do to create your soluble salt. You may see in the exam that to help the insoluble base react with the acid, you may see this acid heated over a Bunsen, just gently, just to warm it up a little bit before this is added. But obviously that's going to have safety precautions associated with it, because you're heating acid and you don't want that spitting out of the beaker. Also here, when you're heating the crystals, this must be very gentle heat, otherwise they can end up drying out too quickly and spitting at you as well. Now we're going to look at the reactivity series. The reactivity series is how we list metals in order of their reactivity. So here we've got potassium, which is most reactive, and then copper, which is least reactive. Copper is really useful because it doesn't react with many things. It doesn't react with water, so you can use it as water pipes and things like that. Also, not on this list, but you'll find substances such as gold. They're completely unreactive, which we'll talk about later when we're talking about extracting metals. Within that list as well, you'll also have two non-metals. You'll have carbon and hydrogen that you need to be aware of. Again, important for metal extraction a little bit later on. You may well be asked to have a look at some examples of experiments and work out the order of reactivity. For example, if we had some potassium in this conical flask over here, this would react with water quite vigorously. In fact, potassium would float on top of the water because it's got a low density from group 1, and it would react vigorously, perhaps producing a flame as well, and fizzing around on top of the water, producing lots of hydrogen gas. That would show that that was really reactive. You might then have something like magnesium, which you would put in another conical flask. Again, that would fizz quite a lot, producing a fair amount of gas, but not as much as the potassium. And then finally, you might have something like iron. That would give fewer bubbles of gas and would obviously be less reactive. So you might have to have a look at descriptions of experiments and then work out their order of reactivity. Linking into the reactivity series then, we're going to talk about how we can extract metals by the process of reduction, which is a chemical reaction we talked about earlier, which involves removing oxygen. So here we've got the reactivity series again, and this is important to understand what methods we can use to extract metals. Now, apart from metals such as gold, which are completely unreactive and can be found naturally, you can sieve for gold in the river and it won't have reacted with anything else, it's just found in its natural state. All the other ones tend to react with things like oxygen and form a rock, which we call an ore. So this is a rock which contains metals. For example, this rock could be iron oxide. But when coming to extract metals, we need to take that iron oxide and actually take the iron out of that rock. And there might be other impurities in there as well. There may well be sulfur and carbon in the rock and things like that. Now, with iron, as well as zinc and copper, one way we can do this is by a process of reduction. And this can only happen with anything that is below carbon on the reactivity series. So we can't do reduction with potassium, sodium, lithium, calcium or magnesium because they themselves are more reactive than carbon. This is an example. Let's use iron as an example. If we have our ore, which is iron oxide, and we want to extract the iron, we would heat it up with carbon, and that would then produce iron and carbon dioxide, which is the reduction reaction that we looked at when we looked at chemical reactions. It's called reduction because you are removing the oxygen from the ore. If you were to do this with magnesium oxide, nothing would happen because the carbon is not reactive enough to take away that oxygen. So this only happens for metals that are less reactive than carbon. So for example here, you might see in the exam them talk about a blast furnace where they may do this kind of reduction reaction. So in here they would put your iron oxide and your carbon, and you'd need hot air going in here, and out at the bottom you'd end up with your molten iron, and any impurities also come out at the bottom. It's a substance called slag which comes out the bottom, and any of your waste gases will come out the top, so your carbon dioxide and so on will come out the top. Another process in which you can extract metals is called electrolysis. Electrolysis uses electricity to split up compounds. So electrolysis uses electricity to split metal compounds. But the trouble is with electrolysis is it uses a lot of energy because the electricity needed, and therefore it is very expensive. So with the metals that are below carbon in the reactivity series, really you want to be using reduction because that's cheaper. However, some metals such as aluminium, you can't use reduction because they're more reactive than carbon, so you would have to use electrolysis, and it makes it a little bit more expensive. Let's take our basic example first of all, and this links back to ionic bonding. So with our ore, let's say for example here we had lead bromide. Remember back from ionic bonding, we've got a metal and a non-metal bonding together. So this comprises of ions. We've got our lead ion, Pb2+, and two bromide ions, Br-, bonded together to make that compound. Now, if we were to stick two electrodes in there and link it up to a direct current supply, nothing would happen. Because in this state here, whilst it's solid, if you remember from ionic bonding, we've got a lattice structure of positive and negative ions throughout, but the trouble is these ions can't move anywhere. But you can make this molten by heating it up, and when you do that, when you make it molten, those ions are then free to flow. So the bromide ions and the lead ions can then move around and conduct electricity because they are moving charges. This is not talking about electrons flowing in this liquid here. We are talking about ions that are free to flow. So please don't write electrons. Make sure you're talking about ions. This liquid here is called the electrolyte. And these are the two electrodes. You've got a positive electrode, otherwise known as the anode, but if you don't remember that, just write positive electrode, and the negative electrode, which is the cathode. And this, as I'll show you later, is connected up to a DC supply. So in this simple case here, we've got our ore and we've heated it up so it is now molten and the ions are free to flow. Within here we've got positive ions. They will be attracted to the negative electrode, and here we would have lead collecting around the negative electrode. And to the positive electrode you will have the bromide ions going, and they will go off as bromine, which is Br2. And you'll see the bromine gas given off at the electrode. In a second case here, I'm going to talk about the electrolysis of aluminium oxide. Aluminium oxide has an extremely high melting point, which would make this process very expensive. So what they do first of all is they dissolve it in something called cryolite, and that then lowers the melting point, so it takes less energy to heat it up and melt it and make it molten, which in turn saves money and makes the aluminium cheaper. So in here we have a mixture of, well, in this complete chamber in fact, we have a mixture of aluminium oxide and cryolite. That's our electrolyte, aluminium oxide and cryolite. And this time, you need to look at the diagram very carefully, and they'll show you on the diagram. But this time they have 3 positive electrodes at the top. There may be 4, there may be 5, there may be 6, there may be more than that, doesn't matter on the number, but all of the ones going in at the top are now positive electrodes. And actually the negative electrode is the outside casing. So in here we have aluminium ions, Al3+, and oxide ions, 2-. The aluminium ions are positive, so they are attracted to the outside, and then they are tapped off at the bottom. So here you get molten aluminium coming out of the bottom, which you will then collect and use for whatever you want. At the top here you can see the positive electrodes, and this is where the oxygen is attracted to, so you get oxygen given off. But also what happens is, there's a really common question in the exam, These electrodes are made out of graphite, and if you remember, graphite is made up of one element, and that is carbon. So they often ask, why do these graphite electrodes gradually degrade and wear away? And the answer is the oxygen that goes to these electrodes reacts with the carbon, producing carbon dioxide. So these gradually degrade because the oxygen reacts with the carbon to produce carbon dioxide. So in this electrolysis you will also get carbon dioxide given off as the oxygen reacts with the electrodes, and then they gradually need to be replaced over time. There is also a required practical on electrolysis, so be prepared to describe a method to set up electrolysis and also predict the results of the electrolysis. So for this we're going to be talking about electrolysis of aqueous solutions. That's when they are dissolved in water. So not only will you get a particular ionic compound, but you will also get the ions that are found in water. So you need to be able to draw a setup from scratch. So you would need to draw a container and show electrodes going into that container connected to a power supply. When you draw the power supply, the long line of the cell would be the positive, connected to the positive electrode, and the shorter line to the negative electrode. And then you need to show your electrolyte solution covering the electrodes. And you can label those up. So you'd label the electrolyte, which is the liquid that you're using, your electrodes, so your positive electrode or your anode, your negative electrode, and your DC supply. It has to be direct current, otherwise it won't work. So let's say for this example, we are doing the electrolysis of sodium chloride solution. So with sodium chloride, if you were to split that up, you would have two ions, sodium and chlorine. But because it's in solution, it also means that you have the ions that are in water. So you would also have hydrogen ions and also hydroxide ions in that solution. And that poses a problem because you have negative ions, two of them, and two positive ions. So that means that you need to predict what is going to go to the negative electrode and what is going to go to the positive electrode. So in this case, the rule at the negative electrode is the least reactive element goes to the electrode. So in this case, hydrogen is less reactive than sodium, so you're going to get hydrogen gas given off. And with the positive electrode, if there is a halide ion in there, then that will be produced at the positive electrode. If not, oxygen will be produced. So in this case, we've got our chlorine present, so chlorine will be produced, Cl2. If a halide ion, remembering that halide is a halogen from group 7, so if halide ion is present, that will go to the electrode. If not, oxygen is produced because it's to do with the hydroxide ion going to that electrode instead. So if not, oxygen is produced. And I'll show you an example of that in just a sec. So you might need to draw this out, show the ions in there, and predict what is going to be produced. So we've got a hydrogen gas produced. We can test for that using a squeaky pop test. Comes up in paper 2. Chlorine produced. Again, these tests come up in paper 2, but you may see them as well. And to test for that, you would bleaches a damp litmus paper. So you would put blue litmus paper in and it would turn from blue to white. Left in solution then you have a positive ion and a negative ion, so these are going to attract together and produce sodium hydroxide in the electrolyte that is left. So an example then of when oxygen might be produced, again if we had our chamber set up and we had our positive and our negative electrode connected to our power supply. This time, for example, if we had copper sulfate, we would have copper ions in there, sulfate ions, and the ions that are present in water because it's copper sulfate solution. The same rule applies to the negative electrode in that the least reactive element goes to the electrode. So in this case, the two positive ones are copper and hydrogen. And out of those two, copper is less reactive, so copper will collect at that electrode. And for the positive electrode, you've got hydroxide and sulfate ions. As we don't have a halide ion present, we don't have a group 7 ion present, then our rule says that oxygen will be produced. So at this electrode, you will get oxygen given off because the hydroxide goes there and produces oxygen, which is given off, and water, which goes back into the solution. Half equations is a topic for higher tier pupils only. Half equations can relate to electrolysis, and it all relates to the two words oxidation and reduction, but this time in terms of electrons. So oil rig will help you remember that oxidation is loss of electrons, and reduction is gain of electrons. Now this is different to the chemical reaction that we looked at earlier, which is in terms of gaining oxygen and losing oxygen. So this is definitely in terms of electrons. If you lose electrons, you're oxidized. If you gain electrons, you're reduced. So let's look at lead bromide again, where we got Pb2 plus and Br minus in solution. We said that lead would go to the negative electrode and bromine would be produced at the positive electrode. So you need to be able to write half equations for these, which basically just shows what's happening in terms of electrons. So lead ions, when they go to the negative electrode, they gain electrons and turn into lead atoms. So that is the half equation for what is happening at this electrode. And because they're gaining electrons, reduction is happening at the negative electrode. Lead ions are turning into lead atoms. So with bromine, bromide ions lose electrons and they turn into the bromine molecule. So bromine goes around in pairs, so it must be Br2. So we need to balance that up by a 2 there and a 2 there. The other way that you can write this around for the half equation for bromine, you may see it the other way by saying that bromide ions turn into bromine atoms and lose 2 electrons. So for the positive electrode, there's 2 ways that you can write the half equation. Other examples, for example, hydrogen. The hydrogen ions were to go to a negative electrode, there they would gain electrons and turn into hydrogen molecules, which we'd need to balance up. And chlorine, for example, if chloride ions lost electrons, they would turn into chlorine, and again we'd need to balance that as so. Redox reactions is a topic for higher tier pupils only. Again, it involves the two words oxidation, meaning the loss of electrons, and reduction, meaning the gain of electrons. And what you need to be able to do is understand in a formula like this where you have atoms and where you have ions. If the element is on its own, that is an atom. If it's bonded in a compound with a non-metal, that makes the metal an ion. So copper is an ion there, whereas iron is an atom. Iron here is an ion, whereas copper is an atom. So in this case, we've got iron that is turned from an atom to an ion, where it would go into Fe2+, and we've got copper, which is turned from an ion, Cu2+, to an atom, which is just Cu. So in this case, the iron atom would have lost electrons, and therefore that would have been oxidised, because oxidation is the loss of electron, and the copper would have gained electrons to turn back into a copper atom, and therefore the copper would have been reduced. So they might say to you, which species, meaning which chemical in a chemistry sense, has been reduced, or which species has been oxidised in this equation. And you need to look at which ones are turning from atoms to ions and which ones are turning from ions to atoms. These equations are called redox because you have something that is being reduced and something that is being oxidised in the same reaction. Ionic equations are for higher tier pupils only. So when you see a neutralisation reaction like this, you can actually write it as a simpler ionic equation, which only involves the elements that are changing from ions into atoms or vice versa. So in this equation above, because it's a neutralisation reaction and it's producing water, one trick to remember is when it's neutralisation, the ionic equation is always going to be the same. Hydrogen reacting with hydroxide ions to produce water. Everything else are spectator ions. For example, to show you here, the chloride ion here is still a chloride ion on this side of the equation. That hasn't changed. The sodium ion here is still a sodium ion on this side of the equation. So they're both spectator ions that can be taken out. However, you've got here a hydrogen ion and a hydroxide ion that then bond together as a molecule of water. So what we're doing is getting rid of the ions that are staying the same and writing out in its simpler form to show the ions that are changing and reacting. So the ionic equation for any neutralisation reaction is going to be the same. Hydrogen ions plus hydroxide makes water. You can also write ionic equations for displacement reactions and other reactions in the topic. But let's have a look at displacement. We'll look at the elements that are changing between ions and atoms. So in this case, we've got a magnesium atom, and now it's bonded, it's now an ion, so that's going to be changing. We've got a zinc ion, which is changing into a zinc atom, but the chloride ions are staying the same. They're bonded this side, they're an ion, they're bonded that side. So they're spectator ions that can be removed, and we can write an ionic equation which shows magnesium atoms react with zinc ions. Zinc is Zn2+, and they will produce magnesium ions, Mg2+, and zinc. And one more example here, you've got iron atoms that turn into ions and copper ions that turn into atoms. The sulfate ion we don't need to worry about because it's a spectator ion, it stays an ion both sides. So our ionic equation getting rid of the spectator ions would be iron atoms, add copper ions, producing iron ions and copper atoms. Topic 5 is quite a short topic on energy. It includes a required practical and also another calculation which is for higher tier only. We'll start off by talking about exothermic and endothermic reactions. Exothermic reactions give out heat to the environment, or the surroundings as we call it. So exo, like exit, you're going out, so that might help you remember that exo means give out heat to the surroundings. And there's several different reactions. Most reactions are exothermic, so things like neutralisation reactions when you add an acid to a base. Respiration is an exothermic reaction. Energy is released during respiration, so it's an exothermic reaction. Metals and acids. Anything that gets hot shows that the energy is being released to the surroundings. These have several practical uses as well, for example in things such as hand warmers or self-heating cans, where you can initiate a chemical reaction and heat up food. Endothermic reactions are the opposite. These reactions take in heat from the surroundings. So endo means take in heat, whereas we said exo means give out heat. Typical reactions that are endothermic are things like thermal decomposition reactions. Looking at their name, they use heat, thermal, to decompose or break things down. So they need to take in heat to break down particular chemicals. Photosynthesis, which is the opposite of respiration, is an example of an endothermic reaction. And practical uses are things like sports injury packs. So in here you will have an endothermic reaction which you can initiate and then put on an injury, and you can imagine if you've hurt your knee or your leg, there's going to be lots of heat from that injury which can be taken in by the endothermic reaction, which will then cool down your injury and help it feel better. These diagrams show reaction profiles which show the overall energy transfer in chemical reactions. You have two lines on these. You have the reactants and the products. If you remember, all the chemicals on the left-hand side of an equation are the reactants, and they produce products. So in this reaction, in these reaction profiles, you just have to say what you see. You've got the progress of the reaction and energy. So in this case, the energy of the reactants is lower than the energy of the products. This means energy must have been put into the reaction because the products have more energy. So this reaction profile shows an endothermic reaction, whereas with this one, again, say what you see, the reactants have more energy than the products. So energy must have been given out, so this is an exothermic reaction. When you're asked to explain why it's exothermic, you can say that the reactants are higher than the products, so they have more energy than the products, and the opposite way around for this one. So there's a couple of key points. You need to label these very carefully. If you're asked to label the activation energy, make sure you are doing so from the reactants up to the product, to the top of the products, and the same for this one here. This I'll label A, but it's the activation energy. This is the minimum amount of energy needed for a reaction to happen. And this comes up in paper 2 when you're talking about collision theory as well. So A is the activation energy, and the other thing that you might have to label is the overall energy change, which I'll just call delta H, because that's what we normally call it. Overall energy change, and that's the difference between the reactants and the products. So here, this is the overall energy change, and the energy is going up, and in this case here, you need to make it as exact as you can. This is the overall energy change, and the energy is going down. So in this case, the delta H is negative, and this case the delta H, or the change in energy, is positive. The only other thing that you might be asked to do is show the effect of a catalyst on these diagrams. A catalyst provides an alternative pathway with a lower activation energy. It tends to come up in paper 2, that definition, but here we can show an alternative pathway with a lower activation energy. So it's got to be lower than the activation energy here, and in the same way on this side to show the catalyst. Now we'll discuss a required practical on exothermic and endothermic reactions. So with this practical, you'll be asked to investigate the temperature change of a reaction, and you might be asked to change a particular variable such as concentration or mass of the reactant and see what effect that has. The main thing with this practical is the reaction happens in a polystyrene cup, and you'll have a thermometer in there to see how the temperature changes in the reaction. But the main thing that they'll ask you is how to improve the apparatus in the equipment. The main things they'll miss off are a lid on the cup. Okay, so we must have a lid here, and also a lid on the beaker would be preferable, with the cup surrounded by some form of insulation. So they're the main improvements that you need to look for. Has it got insulation? Has it got a lid to prevent heat loss? Or in terms of endothermic, heat actually going into the practical. So for example, if you wanted to look at an exothermic reaction, you could either do a neutralisation reaction, or you could, for example, put a metal in with an acid, and when you do that you'll see a temperature rise, and you can measure that on the thermometer. You might want to change the concentration of the acid, for example, maybe use 0.1 molar, 0.2 molar, etc., maybe up to 1 molar, and then you could see the effect that that has on the temperature change in the reaction. You could also do an endothermic reaction if you wanted to. For example, you could have water and something like potassium chloride. You could put those both into the cup, and you could measure the temperature decrease this time in the reaction. And for potassium chloride, you might want to change the mass that you're using. So maybe start with 5 grams and then use 10 grams, 15 grams, etc. and see the effect that that has on the temperature change. So bear in mind that you might be asked for improvements in this investigation, or you might be asked to write a method from scratch for a particular reaction. If you're doing a neutralisation reaction, for example, maybe you're reacting hydrochloric acid with sodium hydroxide, for example. If you're using these two liquids, you must make sure that they start at the same temperature. So you might want to put those in a water bath, say at 25 degrees C before the reaction, and then you know that they both have the same starting temperature, and that means that temperature is therefore controlled before the reaction begins. Bond energy calculations are for higher tier only, and what you need to remember for these calculations is that energy is released when bonds are made, and energy is needed or taken in when bonds are broken. So the second line is more easy to understand. So to break bonds between atoms, you need to put energy in, so energy is taken in, that makes sense. And this other one is the opposite effect of that, which is slightly harder to get your heads around. But whenever a bond is actually made, energy is released. So we can calculate the overall energy change in a reaction. In an exam, you'll be given the equation. Make sure it is balanced. Normally they will balance it for you. They will give you the displayed formulas for the chemicals in the equation, and they will give you a table that shows the bond energies. Now these are constants. You can look these up on the internet. and you will be given these in exam. So for example, the energy needed to break a CH bond is 413 kilojoules per mole. Alternatively, this would be the energy released when that bond is made, depending on whether you're making the bond or breaking the bond. So with bond energies, you need to add up all of the energies, all of the bond energies on the left-hand side, and then all of the bond energies on the right-hand side. So in this case, they've given you the displayed formulas, and they will do in the exam. So you need to make sure you circle all of the bonds and add all of them up. So here we have 4 CH bonds. So CH has a bond energy of 413. So we have 4 lots of 413. And we add that to 2 O double bond O bonds, which have bond energy of 498. So 2 times 498. And on this side, again, make sure you circle all the bonds so that you don't miss any out. You've got C double bond O, C double bond O. So that's 799. So 2 lots of 799. Added to 1, 2, 3, 4 OH bonds. So 4 lots of 4, 6, 3. And be really careful. You notice when I was writing, I nearly made a mistake there. You need to copy these numbers carefully from the table, otherwise you'll lose all of the marks. So if we add that up on the left hand side, we've got a total bond energies of 2648, and on the right hand side a total of 3450. That will get you a couple of marks. Your final steps you need to do is take 3450 from 2648, so do this number minus that number, and that gives you an answer of minus 802 kilojoules per mole. And that number there is the overall energy change in the reaction. And because it's negative, it gives you the clue that that is an exothermic reaction. If you remember back from the reaction profiles that we looked at, that means the reactants have more energy than the products. So the overall energy change here, delta H, is negative, hence that negative value there of minus 802 kilojoules per mole. So when you do this last calculation, it may well be a negative number or it might be positive.